other one by one. And what I can see is that if I just use the simple architectures, I get a quite low error for the first 10 digits, and that means that input reconstruction is bad with respect to the one that was the original input, and I showed you that. Also, if I use the mean digit and the filter mean digit, the error increases because I'm comparing that to the first 10 digits original input that I had, and the error is going to grow up, but eventually it's going to be still a low error, so we have the reconstruction. If I instead see the hybrid internal representation, what I get is a higher error when I don't use the F mapping, and always, I stress this, always a lower error compared one another when I use the F mapping. And that means that something has been reconstructed. We have a few exceptions. I want to point that out here. One, and I can't remember what, but it's just a few samples. So, discussion and conclusions. What I wanted to show was that the DBN, the deep belief network, stacked autoencoders and stacked denoising autoencoders were very similar. And I think that with respect to some parameters like robustness noise, pruning to overtraining and so on, we've showed that they are really similar to each other. So they're almost interchangeable, and it depends on the experiment set to which algorithm is more suitable for the experiment, but the outcome is going to be the same. The difference happens layer-wise when the training is performed, so the fine-tuning is the same always, and those differences in the layer-wise training are not affecting the final internal representation, because I showed you that using the F mapping, they are also quite similar to each other. So that allows for the hybrid approach I was describing before. And what we can reflect on is the fine-tuning stage. So that is really required by the machine, deep learning approach, and is always used, but that's gonna ruin the ability of the deep network to do the backward operation, so reconstruct some internal representation into inputs. And that's all I want to point out. So, thank you.
Thank you.
Well, first I want to start by saying good job.
Thank you.
This was a very comprehensive paper to read. I appreciate that you didn't settle for just using one metric of comparison to these networks, but you went further and further and further, as if you were disappointed by not finding anything with the previous method, so you added more and more and more until you found something. So that was very nice to read. So you went with the noise. I think that was a good measure. The standard accuracy, yes, that's obvious. The sparseness I thought was very good because it's specific to autoencoders, so measuring that was indicative of how well the network can store that information and reconstruct it. And especially I really enjoyed these, the representation, the layers and the internal filters, the visualization. That was very interesting to me to see. But so I have a few questions though. So just by reading the paper, I understand the main purpose was comparison between these architectures. But what is there a specific type of data that these networks perform better than any other architecture? So what is so special about these networks?
Yes, so it has been tested in literature that they can perform with a lot of different kind of data, especially the deep belief network and the stacked autoencoder are not tied to images. So we can get the images as the input layer as vectors actually. Mm-hmm. So they're presented as image that a human can watch, but they're immediately not pre-processed and used as vectors. So eventually any vector of values can be fed to these deep networks, and I think the outcome will be pretty much the same. The NIST dataset I use is the one that's used in literature, and it's the standard to test these machines. So I think it was wise to use the same dataset in order to have some very general results on this. And of course, further study can apply different datasets and see the results.
Yeah, so that was my next question. Why choose an image dataset? Because this is typically convolutional networks are better than these types of networks with images.
Yes, because it has been proven before that those two networks were working on digit images. So I chose a database that was good for a human to understand at eye, because if I want to feed the internal representation and reconstruct them in input, and we were using some dataset like electroencephalography data, a human could have sorry, my English, couldn't have possibly understood what the meaning of the reconstruction was without some numbers. And I think this was better for the report, actually. So that's the choice.
Perhaps trying another type of data together with the image would have added value to the report too, because then you test the same network on different types of data, and you test it on 3 types.
Yes,
of the
totally.
But I understand why the whole point of the visualization, which was the highlight of the report, could have been possible on other data.
Yeah, it depended a lot also on the first results, because if I had time to explore the first results on different datasets, it would have been nice to do with your approach. But once I saw that proceeding with the same dataset was giving more and more interesting questions while proceeding, I preferred to stick to that dataset and explore the further questions until to the F mapping that came out. And I think I appreciate that result. So I'm proud of that approach. Sorry, I want to say that. Yeah.
So I have a question about the F mapping.
Yeah.
Can you go back to slide? Which was it? The one where you explained the first. Oh, page 42.
Yes. 42 this.
Yes. So first, why did you decide to choose the first 3 and the last 3 pixels?
Yes, because actually it's when I told you that what I'm representing as images every time is a vector of values. So by the point of a programmer, if you think about the first 3 and the last 3 pixels of an image as a vector, you're gonna take the first 3 values and the last 3 values. So that's very easy to pick. And if I wanted to take the whole border, which was my aim, I should have done some mapping for the border over the vector of elements, and that would have taken time. So I went for this approach, and this resulted in this normalization, which looked quite good. So I didn't want to have more background in the mean.
But this makes some assumptions about the nature of the tiles. So
yes, I assume that the features, actually by experimentally looking at the feature itself, you can see that all that appears is in the circle at the center of the image.
Right, because this is by nature.
So probably the square around that circle is going to be a sort of background, and more in the corner, like if you put a circle here. So what I was interested in was this triangles in the 4 corners as a background.
Do you feel that this would also be the case if it was trained not on image data, but...
I'm sorry?
Do you feel that this would also be the case?
Yeah.
Like picking the 2 corners as valid points to do normalization? If it was not fed with image data, the network, because images, particularly the one in MNIST, they have white background and the digit center in the center.
Yes, but if it was, yes, but I can answer that question in a different way. If it was some different kind of data, I would have known how to normalize that. For instance, if it was an electroencephalogram, I could have fixed the range of the amplitude, and I could have said that the normalization was to put the zeros in the amplitude, and that would have been my background value, the 0 level. So I wouldn't have needed to do this kind of image approach to the background. And
so perhaps as a more generalized step, you can just say pick the normalization method appropriate for your data.
Yes, totally. Yes. The normalization is related to the data,
right,
not to the F mapping idea. But it's needed. It's needed because if I don't do that, I'm gonna compare, and I did that as an experiment. I'm gonna compare more. I'll show you. So, yes. In this case, if I'm going to compare these styles together, no matter what I do, this style is going to be compared more to this one because the overall image looks similar, even at sight for a human. So you won't look at the feature inside, which is so small, but you will look at the overall image, and that value, overall value, is going to say that this style is going to be more close to that, no matter what's inside. So I wanted to avoid that in the F mapping. I really need to focus on the features inside. That's why the normalization.
Okay. I have one last question.
Yes.
If I remember from the report, the way you did the mapping, so you have 4 filters here and 4 filters here, and you compare them by after normalizing by saying, so I will take this from this set
Yes.
and find the closest one from this set.
Yes.
And then, so that the closest one is here, and then I'll remove these two.
Yes.
And now I have these left.
Yes.
But I think it would be better if you compare all of the filters to each other, because by removing this filter only by comparing to the first one, you've never compared this to the third one.
No, I'm doing that because
Okay.
I'm not sure I can show you the animation was meant to be like this. So I'm gonna scan the whole image on the right for that filter,
Yes.
and then I'm gonna switch to the second, and I'm gonna scan the other set
Okay, so
again. All. So what I get in the end is that I've scanned for each filter of this set all the single filters in the other set. And what I get in the end is the best match for that round. And those two tiles are excluded by the two matrices, and the algorithm proceeds in the same way with the remaining tiles until I get all of them. And I told you that when I do the sorting, those are the best matches in this part, and those are the worst because of this approach. So probably there's going to be a better approach, and even if I can get better filters in those two cases, probably the first filters are too many for the data I fed. So if the filters were a good number to be really the same ones for the whole matrix, then I could compare them exactly and get an exact mapping between the two representations.
Okay.
This is very interesting.
Yeah.
Thank you for the question.
Any
Yeah, thank you.
other short
Yes,
question or
Can I
comment?
ask this question?
Yes.
To me, these filters, they look quite arbitrary. So would it still have worked if you put any arbitrary filter in your hidden layers and train the last layer? Would it still work?
Can you ask in a different way? Sorry.
If we look at these shapes,
Yeah, you say they're quite random.
they are quite
But-
arbitrary shapes. I mean, they are continuous functions of some sort,
Yes.
but they are biphasic and so on. So if I randomly start with some filter,
Yes.
put it in the internal layers,
Yes.
and then train only the last layer.
But the thing is, the filters are not in the internal layers. They are
In the
some
connections.
emerging. They are some emerging effects